In this video, we're looking at a basic electromagnetic induction problem. We're given a flat coil with 500 turns in it. The average diameter is 25 centimeters. Of course, we'll have to change that to meters. That's 0.25 meters. And we're told the coil terminates with two banana plug terminals, and we connect a voltmeter to it. Then we turn on a magnetic field with a strength of 0.33 Tesla. And that's perpendicular to the plane of the coil, and it takes a quarter of a second, or 0.25 seconds, to reach its full strength. In part A, we want to get the flux per loop when the magnetic field reaches its full strength. And I'll post a link to where this was first introduced, but the formula for the flux goes like this. Again, this is the flux for just a single loop, and that's given by A, the area of the loop, multiplied by B, the strength of the magnetic field, times the cosine of theta. And what theta is there is the angle between the normal vector for the loop and the magnetic field. The normal vector is a vector pointing perpendicular to the plane of the loop, and we can see that that's parallel to the magnetic field, making the angle theta 0, and the cosine of theta is equal to 1. So all we need to do is multiply the area of the loop by the strength of the magnetic field. Because we're given the diameter of the loop, instead of writing area as pi r squared, we'll sub in d over 2 for r, and when we simplify, we get an area of 1/4 pi diameter squared, and then the strength of the magnetic field, that's still b. So we plug the numbers in. Here I'm changing the diameter to meters, and when we run the numbers on this, we get 0.016199 Tesla meters squared. And I usually round things to 3 significant digits, so we'll write it as 0.0162 Tesla meters squared. In part B, we want the average induced EMF read at the voltmeter. So we have a changing magnetic field through these coils. We know that an EMF is induced in a direction that opposes the change in magnetic flux. And the formula for this is normally written like this. E induced is negative N delta phi delta T. So delta phi over delta T is the rate of change in the flux and is the number of turns in the coil. The minus sign indicates that the direction of induced EMF is to oppose the change in magnetic flux. All we really need here is the magnitude of the average induced EMF. So we're ignoring the minus sign. And we have 500 turns. And the change in flux for a single coil we just computed as 0.0162 Tesla meters squared. And the time it took for this magnetic field to turn on was given as 0.25 seconds. When we run the numbers on this, we get 32.4 volts for the average induced EMF, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.